Okay, great. I think we can start now with the correction of the second masterclass. So Wojtek, if you want to share your screen, then you can go.
So, ladies and gentlemen, welcome. Do you see my screen?
Yes.
Great. And my mouse cursor?
Also, yes.
Perfect. So I will start. I will ask first if you had some problems with installation of programs or everything was smooth. Was there any there were any problems with installation? It was there were some difficulties to install R or RStudio or Metadynamics. If somebody experienced them.
I never used before, and it was smooth, so no problems.
Great. Great to know. I also mentioned last time that, for example, you can use Metadynamics if you are if you do some calculation at some, for example, high performance computing center, and you don't want to download Hills files, so instead you can run the analysis in at such a center, and usually I would guess that sometimes R can be installed because it's like some basic Linux package. So I would expect this to be usually installed there. And if not, it would be necessary to ask some administrators or make some own installation. And for packages, like if you have some general installation of R at some multi-user computer, like some computer cluster, then it usually installs in your home directory, like your separate or your own like version or own installation. It's not possible for other users to use it, but you can do it even if you don't have some privileges to install some program at some computer. So if everything was okay with installation, then great. I mentioned last time that if you needs to find some help, then there are in R there are like two possibilities. So for some function, you type help and in brackets the name of a function for which you want to find the help, or equivalent is like question mark and the name of a function for which you want to find the help. What I forgot to tell you, and what came to my mind when I was preparing this, that maybe if somebody was looking, for example, that you used a plot function to plot FreeEnergySurface, and then you wanted to somehow like add some change the name of axis or something like that, and you needed help. So if you type like question mark and plot, this will give you some very basic help to general plotting in R. The reason is that the function plot is like they call it generic function, which means that there are different variants of the function plot depending on what type of object they are applied. So if you, for example, use plot on FreeEnergySurface in Metadynamics, it will give completely different output than if you plot some function or if you plot some dendrogram from some hierarchical clustering or some other type of object. So for this, you have to type like plot, like question mark plot and dot and the name of object. And if you don't know what's the object, so in Metadynamics FreeEnergySurface is like object called fes. So it's possible to type like plot and then press tabulator, and it will give you some hints. So this is something like which can somehow make finding help a little bit more complicated. And Unfortunately, this is something I'm not very happy with, but also in Metadyn miner, some functions which are specifically for Metadyn miner, they are such a like a generic function. And this is because like first I made Metadyn miner, and the second I made Metadyn miner 3D for 3-dimensional free energy surfaces. And for this reason, it was somehow necessary to make like this original function such a generic, and that they work in two different ways depending whether they are applied in one package or the second package. But I believe that the help is in this case equivalent. So if you type, for example, this function fes minima, if you type question mark fes minima, it will give you exactly the same help as if you type question mark fes minima dot fes. So, but for this plot and some summary, it's also another generic function which is used in Metadyn miner. Plot and summary. These are functions which, if you want to find a specific help for these functions, then you have to type question mark, plot, and the name of object, and not just plot or not just summary. So what was the source of data for this tutorial? So I made some very simple well-tempered metadynamic simulation of alanine dipeptide. Alanine dipeptide is kind of molecular hero of many different simulations, especially enhanced sampling simulations, and original metadynamics paper from 2002. There will be anniversary soon. So it was also one of objects studied was alanine dipeptide. And it is like a kind of amino acid in which, or something system which mimics the state of amino acid inside protein. So it's amino acid alanine, which is kept by acetyl on N-terminus and N-methylamide at the C-terminus. And you can express its conformation by torsions phi and psi here. And the distribution of phi and psi in solution of alanine dipeptide is pretty similar to the distribution of values of phi and psi of different amino acids in proteins. So if you take some protein and for each amino acid residue, calculate phi and psi and make some plot, scatter plot of phi versus psi, so-called Ramachandran plot, then this is very similar to distribution of alanine dipeptide in water. There are some energy barriers of some conformational changes. So if you run something like nanosecond simulation, you are not likely to explore all relevant conformation and to get some realistic distributions of different states of different conformers of alanine dipeptide. So for this, you need to calculate metadynamics, so either well-tempered metadynamics or some other enhanced sampling method, and by this in some nanosecond time scales you can get quite nice free energy surface. And there were different inputs. So if you were interested, it was on the text of the tutorial there is a link to Zenodo, where there are all the input files for just reference. But we were working here just with the output with Hills files and a little bit with Colvar files. So I will start with Hills. So just to summarize how Hills are written in PLUMED. You got some header and then the list of hills. On each line there is a single hill. In the first column there is time in picoseconds. Then in our case there was phi and psi torsion, so there is phi and psi. The widths of phi and psi, or the sigma values, I used 0.3, which works pretty well for torsions. So because there is the range is from minus pi to plus pi, which means something like slightly above 6. So this is like approximately 5% of the total range of the collective variable, and it works reasonably well. And the most important are heights of hills, which are different because we use well-tempered metadynamics. And I set the height of hill 1 kilojoule per mole. And here the height of the first hill is 1.07 something. And this is because this height is already like pre-scaled by bias factor, which was 15. So it's multiplied by bias factor and divided by bias factor -1. So this gives like this value. So all these values are not exactly like the heights of hills in which are used for flooding, but they are already pre-scaled, so they can be easily converted like to summed up and converted to free energy surface. So here is just some explanation in classical metadynamics, which means like before well-tempered metadynamics, which is now used quite rarely, I would say. The height of hills was constant, and so here at the top you see like the bias potential, and here at the bottom you see the flooding of the free energy surface of some free energy well. And if you flood such a free energy well, then this bias potential added to the free energy profile should be approximately like flat, horizontal. There could be some noise, but there should be no like convexity. And in contrast, in well-tempered metadynamics, because like the heights of hills are being scaled down or lowered depending on the bias potential accumulated. So in the center, where there is a lot of bias potential, the new hills which are being added are small. On the other hand, at some edges where there is no bias potential, this new bias potential is as the original height. So the result is that this free energy surface is the bias potential is slightly lower than in classical it's like this flooding of this by this bias potential makes that this level of the flooded free energy surface is a bit like convex, and it's necessary to multiply it by the bias factor and divide by bias factor -1. So in our case, because bias factor was 15, we multiply it by 15 divided by 14. And this is how MetadynMiner basically works, that it simply sums hills which are used to define the bias potential. So I will go through some functions that we used, and I can maybe show some other ways how to use them, or some other options and some maybe pitfalls what can go wrong. So first I will start with this this function read hills, which is like in basic R, there is a basic function for reading of some tabular data is called read table. So as an analogy, I give the name of this function read hills. And similarly to read table, you have to specify the file name. As I mentioned, you can have either file in the same directory, in your working directory, and you can download it or load it from your working directory, or if it's somewhere else, you can specify the full path to this directory on your computer and to the file on your computer. Or as a last alternative, it's possible to have some file which is posted on some website, and it's possible to use some HTTP as something like the address to the file. I would ask, did anybody have some problem with loading files or with this working directories and things like that, or was this everything was clear in this? Yes, I see microphone switched on.
Yes, it's fine.
It works. Great, great. Some people advise, like, if you do some some exercise in R to make some separate directory in which you do all the exercise, where you have the source of your commands, and you have some separate subdirectories with data, and then you can pack everything nicely, send it to somebody else who can work on that, and there are no some reproducibility issues. So in this case, it would be necessary just to add like some directory data / and hills, if you prefer to do it in this like tidy way. It depends on how you prefer to organize your data. And there is another option, which is like periodicity, and it's necessary to specify periodicity of collective variables. And I was at the beginning trying to decide at which point this would be best to specify this periodicity, and I found that maybe best option is to specify it really at the beginning when loading the file. So at this point you specify that collective variable 1 and collective variable 2 are periodic, which means like that you specified by a vector with 2 elements which are logical values true and true. So of course, like if just one of them is periodic, then it would be true and false, or false and true, depending on which CV is periodic. You can also specify like this periodicity. So by default, it's from -pi to +pi, like a torsion. But of course, you can, for example, run Metadynamics in plumed input. You can use some simple combine keyword or something like that to convert your torsions from radians to degrees, and then you can run Metadynamics in degrees if you like. So in this case, you would have to switch this to -180 to +180, or to some other relevant values. So this is separate for the first and the second CV. By default, both of them are, if they are periodic, they are from -pi to +pi. By default, like if you use read hills without this option, then it assumes that both CVs are not periodic. And another option which is there is like ignore time, which means that you, very often, if you run some long metadynamics, like some funnel metadynamics, for example, and you have some limited computational resources, so that you have to run it in multiple runs. So it may happen that in your hills file there are many like restarts where the hills from the previous course of the simulations are taken into the account, but the hill numbers are restarted again from 1. So that the actual numbers of hills or time does not correspond exactly to the real time in the simulation. So this may be a problem for some visualization. For example, for calculation of free energy surfaces, this is not big problem. But if it is problem for some other functionalities of Metadyn you can simply use ignore time, and then each hill is like, instead of time, you use the hill number. So the first hill is number 1, second hill is number 2, and instead of some time in picoseconds, you use hill number. So that was ignore time. As I mentioned, in Metadyn there are 2 functions for calculation of free energy surface. One is FES and second is FES2. The difference is that the first one is quite fast. The second one is more accurate. The first one works in a way that you take this free energy. So you take the hill. This function is available only for data where there is a constant width of hill. So the sigma is the same for all hills, which in 99% of metadynamics application is the true. So if you have this condition fulfilled, then the program like calculates like a single hill, and then instead of recalculating the Gaussian function, so doing all the exponential stuff, so it uses this pre-calculated hill and just shift the pre-calculated hill on the canvas of the free energy surface and just sums the value. So this is much more faster. Last time when I was introducing this, I introduced also our web service Metadyn view, which was developed by my former student Petr Hošek, who also came up with this very clever way to calculate the free energy surface from the bias potential. This calculation is a bit approximative, so there could be like some errors from just neglecting some granularity. So for the purpose of some reference calculations, it's better to use this function fes2, which is written in a way that it evaluates the Gaussian function explicitly. So it makes this there is this function evaluated explicitly. Both these functions are, even if this fes2 is much slower, it's, I think, still reasonably fast. So you can, for example,
I have a question.
Yes.
With real data, can you tell me the difference in time? Because I tried both of the functions and it wasn't a really big difference, but maybe because the files were a little bit small.
So
have you tried this with big data, with big amount of data?
I will try to show it on the next slides. So if I answer your question in the next few slides, then okay. If not, I can continue with your question.
Okay.
Okay.
Yes.
So before I do this, I will just remind that it's possible to set like some range for which these hills are summed. This is not very useful, like especially it doesn't make sense from the physical point of view to sum some late part of metadynamics. So because this does not approximate the free energy surface, if you sum it for like last 1000 frames from 10,000, this doesn't make sense, but it's good for some visualization and animation purposes, so that you don't have to like calculate everything from beginning. So and so this changing of this I min can be used for this purpose. This Imax can be useful to see the progress of metadynamics. You can also change the range of free energy surface, like the CV values, CV value range. But by default, it is somehow automatically decided. If the function is periodic, then it's the range of this CV. If it's not periodic, then this is some like highest and lowest point in the CV space, or highest and lowest value of certain CV is taken, and then it is a little bit extended to both sides. If you use this free energy surface calculated on too small, or if you use it on some smaller area than at which you print it at the end, then the rest of the free energy surface would be white with no data. And one thing which can be maybe helpful is the number of points. So if by default this is 256, so you got 256 times 256 points in a matrix where these free energy values are calculated, stored. So now to this comparison of the function, so I will first start with the speed. And there are in R, there are several packages for some benchmarking, for calculation of speed of different operations, but the simplest one is just this one, that you somehow save your system time before and after function execution, and then you subtract it. And here on my laptop, from which I'm just broadcasting, and from the same data, it was like 1.4 seconds for this function fes, and 18 seconds for function fes2 with 10,000 hills. So I think it's quite reasonably fast, both of them. Of course, like for some animations, it's much better to use this fes function. And if we compare them, like we can subtract these free energy surfaces. Here there is a warning. If you do some operation of free energy surfaces like subtraction or multiplication by some constant or something like that, you would get such a warning. The reason is that like when I was trying to somehow design all the functions and their communications, there were like different possible scenarios how to do it, and I wanted to make it as simple as possible for users. So the result is, for example, that if you calculate the free energy surface, the hills data, hills positions are somehow stored in the output. And then if you find free energy minima, they are still stored in the output. And then if you calculate this profile, these hills are used to calculate the profile of like free energy differences versus time. So for this is the reason why these hills positions and heights and widths are stored along different operations. But if you do some operation like subtraction, it's not possible to make some hills which correspond to like subtracted free energy surfaces. So then there is a warning that you should be very careful if you, for example, from this difference would use by some other function, for example, to calculate the profile of evolution of the free energy surface or free energy differences as a function of time. So that's just explanation why there is this warning. And if you want to get like I would say naked free energy surface, I will get to this point a little bit later. So you can somehow like get some instances of the object which stores free energy surface. So and you calculate the minimum and maximum, then it is from -1 to +1 approximately. So there is like 2 kilojoules per mole difference between the lowest point is somewhere here and the highest point is somewhere here. This is, and the range of the free energy surface is from -85 to -11 kilojoules per mole. So this is not negligible. It's quite some value. But I believe it's quite okay, because if you if you first such a difference is not somehow like I would say visible by naked eye in most cases. So for some movies and things like that, I think this is reasonably accurate. And the second, if you look, for example, at this difference, so I plotted this difference here. So here, like contours are every 0.2 kilojoules per mole, and you see that some highest and lowest values are around, or biggest differences are on some edges, or not on edges, but mostly on some. If you look at the free energy surface, like on some slopes. So, which means that the slope is a little bit like shifted in a certain way, rather than in some minima, you got very, very good. So one minimum is here, one minimum is here, one minimum is here. So at minima, you got very good accuracy. But as I said, like for some like final, if you do some series of analysis, you plot some nice figures, and then you decide to plot a final picture for some publication, then I advise to use this FAS2 because it's more accurate. And also for some analysis, some more where you need some accuracy, then you can use FAS2. This FAS2 we compared with PLUMED some hills, and it's more or less like exactly the same, this FAS2. So we can use FAS2 as a like reference. This is correct. FAS is just with some inaccuracy. And in my experience, this inaccuracy is mostly located on some like slopes of hills rather than at some minima. And usually it's not like something which would be visible by naked eye. It's of course like bigger for some free energy surfaces with some high bias potential. So if we have something like -85, which is something you would rather have lower in some more real system, biological system, some protein simulations, I would expect some less deep free energy surfaces. So then this error would be a little bit smaller. So I would ask you if this is answer to your question, or still I have.
Yes, with the previous slide. So very good.
So thank you. And with the free energy surface, there are possibility to do some transformations. So for example, you can subtract some value, or you can calculate the minimum. So this is very useful function if you want your free energy surface to start from 0, to have the global minimum set to 0 and all the values positive. Then you can simply do this, and it's easy. Or if you want, for example, publish in some American journal, and they prefer kilocalories over kilojoules, so you can simply divide by 4.18, or maybe there is one more decimal place I omitted. At this case, there will be again some warning. This is because, like, if you calculate this plot, sorry for jumping, if you calculate this plot, then there will be this plot will not be in kilocalories per mole. It will stay as it is. So this is just warning that what you did, this division by 8.14 was done only on this like FreeEnergySurface object and not on the original data, which are also stored in this object. As I said, there are some like instances. So in R, it's possible to do some kind of object oriented programming. So you can define some class. In case of Metadynamics, there are some new special classes like for hills file, for FreeEnergySurface, for FreeEnergy Minima, for these profiles and some others. And if we have, for example, this FreeEnergySurface, which is called MyFES1, it's possible to somehow, if you need it, this is a little bit more advanced usage of this. So if you need, you can somehow touch these instances. So in this FreeEnergySurface class or FreeEnergySurface object, there is the FreeEnergySurface itself as a matrix. By default, 256 times 256 points. Here is the number of this dimension. So it's like 256. Here is periodicity, whether it's the first and second collective variable is periodic. Then there are individual periodicities. So if it's from -pi to +pi, then there is an object with all hills stored. Dimension means that whether it's like one-dimensional, two-dimensional, or three-dimensional FreeEnergySurface. And then there are I missed Y. There is just X and Y is somehow I deleted it accidentally, possibly. So there is X and Y, like where are values of collective variables for each of these bins of this matrix. And sorry, I probably made here some mistake. So analogously, you can use the function. So how to get them if you want a list? One option is that you type the name of the object, $, and then you press tabulator, and it will give you this like hints. Or there is also function attributes, which can also make a list. So for example, if you decide to convert the FreeEnergySurface from FreeEnergySurface to probabilities, then you can calculate like I will do it in a simple way that I will make my own copy, which will be called props. And then I replace this FreeEnergySurface, this matrix of FreeEnergySurface, by its values, which are converted to probabilities. So I take minus value divided by K, temperature. This is 0.3 because this is in kilojoules, and exponential. And if I plot it, I get such a plot with probabilities. So this is one way what I can do. There is another way. I mentioned that, for example, if you decide to run Metadynamics in instead of torsions expressed in radians, torsions expressed in degrees, you can do it by changing the plumed input, plume.file, using some transformation to transform degrees to radians to degrees, and then you can use torsions in degrees as collective variables if you like. And you can do it also like in Metadynamics, like on hills which were calculated in radians. You can convert them to degrees. So you would need to change these values of X and Y. And you would simply change them by replacing these values by their values multiplied by 180 and divided by pi. Here, this like this plotting is it's just trick that if you do like simply plot and myfast, then you would get some values like 150, 150, some like more natural values, but from the point of view of angle, it is better to use some multiplicates of 60. So you can, by this option, you would erase axis, so there will be no axis. By these two commands, you add the first axis and the second axis, the vertical and horizontal axis, horizontal and vertical axis, and you specify that you want these labels at values like -3 to +3 multiplied by 60, so from -180 to +180 by 60. And by this, you also like delete this box, so at the end you can use empty function box, and it will make such a plot where you got collective variables in degrees. So if you want to do it like not in the metadynamic stage, but in some post-processing stage, you can use this. And this is another illustration how you can get inside the function, so inside the FreeEnergySurface object or inside other objects used in Metadynamics, if you like. So if you want to plot FreeEnergySurface, you have many options that you can change in the plot function. So plot type can be either image, which means that you would get the same output as here, but there would be no these contours, these black contours. Or another option is contours, which means that you would get contours but no color. It will be just white canvas with these contours. And the third option is both. So this is like default. This is this output. I was thinking about, or I believe that it's possible to like combine like one FreeEnergySurface as this image, and another one as a contour, one top of each on top of each other. But unfortunately, this is not possible. So I will have to check it and maybe make this possible. This call scale is equal to true. You can switch on, like there is a special color scale on the right side. You can zoom in by specifying xlim and ylim, so you can zoom to a certain part of the FreeEnergySurface, and you can also define the range of the free energy. So if you get out of some of these, so if you use xlim or ylim, which is bigger than the FreeEnergySurface, you would get some white frame around. And if you use zlim, which is also out of the range, you would get white places. So this is sometimes useful. I quite often use it, like if there is some totally unsampled region, it's better to leave it white rather than red. So you can demonstrate that it was like not sampled at all. It's possible to add some like a title or subtitle or different titles of label of X and Y. So by default is CV1, CV2, but you can change it to degrees, is phi in degrees, psi in degrees. Like if you want to use some Greek letters or some special alphabet or some mathematical notations, I would advise you to look at some help or some Google something. So to get some hints. It's possible to specify these levels of these contours. So for example, if you want your contours being plot every 10 kilojoules per mole, then you can, for example, set zlim to 0 to 100, and then you use n levels is equal to 10, and your contours will be exactly at some multiplicates of 10. Or it's also possible to explicitly specify, so you can even use some not evenly distributed levels, so you can specify them explicitly. Last time I demonstrated that I told the story that when I was submitting the package, there was in a queue a package called Harry Potter, which calculates some like color scales based on Harry Potter characters. So you can, instead of this color, which is just like a rainbow color without violet, I didn't like violet for this, so I just removed violet from rainbow colors. So if you prefer some different color scheme, you can use it, and you can use many different color schemes available in R. And you can also change some sizes, title of this free energy axis, and some other stuff. In the tutorial, you used the function which is called fast2d to 1d, which means like the idea was like 2-dimensional to 1-dimensional. This is like, maybe it's quite a crazy name of the function. So this is the function by using which you can take a 2-dimensional free energy surface and convert it to one-dimensional, or in fact, this is used on hills, original hills, rather than the free energy surface itself. And there is an option ramdim, which by which you can specify which dimension is to be reduced, removed, whether it's like the CV1 or CV2. So if you set ramdim is equal to 2, it will remove the second collective variable. So how does it work? So it will calculate the free energy surface, and I explain how we can convert this free energy surface to probabilities. So we can simply like take this free energies in individual points and convert them to exponential to minus free energy divided by KT, and by this we get some like probabilities. So this is the probability distribution. And next, we can somehow integrate in each of this line for each value of CV1. We can somehow sum up or just integrate these values of CV2. So this would lead to the like overall probability for each value of CV1. So we get this profile, and then we can convert this profile back to the free energy surface. So this would mean to make a minus KT logarithm of this profile. So this is how it works, and you got this one-dimensional free energy surface. Of course, it would be possible to use reweighting for the same purpose, and it would be probably more accurate and more reliable. But this is the simplest option, and yeah, maybe if you are interested to trying reweighting for the same purpose, I believe that there is some like in the tutorial there is enough information how to do that. So basically this is what we did in the second part of the third exercise of the tutorial, or last exercise of the tutorial. So how we can make some nice pictures. So I will ask you if you have what is your experience with saving pictures, whether you prefer to use like these functions, or whether you were happy with the way how one can save image in RStudio, or if you prefer to use to save some file as some, for example, you can use some SVG or some PDF or some vector format, and then you can use some graphical editor to convert from vector to bitmap at any resolution, or you can submit article with vector image as well. So what are your experience? How did you like or dislike saving images or things like that? Are there any experience or some bad experience, for example? So if there are no response, I believe that it was quite smooth. So this is one of hint to save like 8x8 centimeter quite high resolution image like this. And for animation, you can use this it's like a regular expression to make series of images. So this would make like images starting from 0, 0, 0, 1, and then 0, 0, 0, 2, and so you can make up to 9,999 images. I came across to some package for animations in R. So maybe some of you tried it. I tried it. That there was some like issues with memory if there were too many of these images, but otherwise it worked well. And you can, for example, save it as an animated GIF, which was quite nice. And other option is to really like generate by this generate individual files, and then to concatenate them in I will explain what I did, like that I used the program which is called Mencoder. FFmpeg works as well, or if you are familiar with some other program to just join a series of images to a movie, we can discuss this. I will get to this point a little bit later. So what I want to explain now is like how minima can be identified. And our idea was that if we have some free energy surface with especially if this free energy surface is calculated with some narrow widths of hills, it can contain really huge number of minima, not just 1, 2, 3, 4, 5, but much more. And if there are some hundreds of minima, it does not make sense to identify all of them and calculate their free energy values and populations and things like that. So it's maybe better to keep some number of free energy minima rather small. And also it's good to have like these free energy minima like somehow located in different area, different parts of this area, so to have them like to represent different states of the system. And for this purpose, we develop a very simple algorithm that we somehow split the canvas into like this by this grid. By default, there are 8x8 bins. And for each bin, we calculate the the minimum of the free energy at a given bin. So here, for example, at this point, this is this minimum B. In this second sector, this minimum is either somewhere here or somewhere here, I don't know, but it's checked whether this is the local minimum of the free energy surface, and if not, so this is not local minimum because it continues downward this way, or if it's this one, this is not local minimum because it continues downward this way. So this minimum is discarded, and then here this is another minimum. Here the lowest point would be somewhere here, but again it's downward this way, so this is discarded. So by this we find like a reasonable number of representative minima. These minimas are labeled A, B, C, D alphabetically, and at the point when we run out of alphabet is AA, AB, AC, and follows this way. So you can specify if you want more minima, you can change these n bins, but I think in this case this would not change the situation at all. When you list, if you type just print the content of the object which stores minima, it will give you the list of minima. So there's a minimum number, minimum ID or the identifier, then at which bin it is located. So if we have 256 bins this way and this way, so this is like 79 is somewhere here, like 79 from 256, and this is almost at the top, so it's 237. And the value of collective variables and the free energy surface, free energy value, calculated from as a sum of hills at a given point. You can take this value and convert it to population by minus x minus this value divided by KT, and it will give you some relative population. And if you sum up these populations, so you get sum of these values, and divide this value by the sum, and here we multiply it by 100 to get it in percent. So here the population is 41% of minimum A, 32% of minimum B, 23% of minimum C, and then a little bit of D and almost nothing in E. This can be printed by the function summary. Again, summary is very a generic function of R, so it can be used in many different contexts. So in this case, it's also possible to specify the temperature because we have not specified it anywhere. By default, it's 300 kelvins, but you can specify it here, and the unit of energy, which is kilojoules per mole, and I think there is kcal as well available. So this is a quite interesting question, how to predict populations of different states. So the way how Metadynamics is doing that, and which is the very simple way, maybe not always a very accurate way, is to take the free energy in the point corresponding to local minimum and to compare these free energies. So you can subtract them, and from the free energy difference, you can calculate the ratio between, like if this is state A and state B. So this would give you like that there is 90% of B and 10% of A. This is very simple way how to do it, very easy to use, very intuitive. Like if you go to some textbook of any any textbook containing something about reactivity, you would find there such a similar plots, like that you get some energy levels and their energy differences. And So this is quite straightforward to use this method, and that's why we have chosen this method for Metadyn As an alternative, another option would be to calculate like probability in each point of this free energy profile, and calculate it separately for one well and from the second well. And then you can sum up probability for each of these well, and you can compare these probabilities. And from this, you would get again like some free energy difference. So by calculating probability, I mean like calculating exponential to minus free energy divided by kT. So when these two values would differ significantly, so I would say if you have some very low free energy differences, so if you have some, for example, biological system where you have some tiny free energy differences, then there would be a difference between a result calculated by this way and this way. Also, if you have some like different shapes of minima, if you have some very wide and very narrow minimum, then this could also make an impact. On the other hand, if you have some very high free energy differences, then this impact is very low. So this second option is not available at the moment in Metadyn directly, but with your knowledge, you can do it like somehow you can use different functions to do that. And the third option, I think probably most accurate, would be reweighting. So I will talk about reweighting a little bit later. So the one of the last functions that I have presented was this calculation of the free energy profile. And this free energy profile, how this is calculated. So for each of this minimum, for each of this point, we calculate the free energy at this point for different times along the simulation. And then we calculate it for A, it is always 0 because we subtract A from A. And then we subtract B from A, so we calculate the relative free energy difference between B and A, C and A, D and A, and E and A. And this is how the profile looks like. So the B, the blue line, sorry, A, the blue line is always like a constant, 0. And then these other minima, it's like fluctuating. So this bluish would be B, green C, D would be yellow, and E would be red. So you can see that these profiles are quite like steady. They are not somehow like diverging. They are not changing much. So from this, you can assume that the free energy surface calculation is relatively converged. Last time at this point, I advised you to go to the tutorial by Gareth Tribello with some calculation of statistical evaluation of the results of metadynamics or simulations in general. And here you can, if you use on the same same object, the function summary, then this will give you like the same output as for the minima. And beside this, there would be like this free energy difference. So free energies calculated like the minimal and maximal value of each free energy minimum. And here I have set that I want it from the point 6,000 from the 6,000 hills to the end of simulation. So it would calculate it like the minimum and maximum in this range. So from this, it's possible to see that simulations are quite, all the simulations are very well like converged. Of course, like this is not the ultimate proof of convergence, and for this I would advise you to go to the tutorial of Garrett. So now I would just briefly come through these exercises. So the exercise 1, like all the instructions were there. There will be nothing like no blank parts, nothing to fill. So I believe that I have explained most of these functions so far. I have not explained much this notched elastic band. Last time there was an interesting question like how this notched elastic band method works, and yeah, it's calculates the most favorable pathway from one point to another point, and here just on the free energy surface of CV1 and CV2. It does not find like some multidimensional pathway, like something that you can get in some Gaussian program or some other specialized programs. For plotting, here is a way how to do either publication quality image or how to make a movie. And for animation, there are two possibilities, and I believe other options are available, and many of you use some other options. So I came across some package which is called animation. So at this website you can see some tutorial and you can try that. Or another option is to calculate like the to generate series of images, and from this series of images it's possible to concatenate them into movie. And for this purpose I use the program which is called Mencoder, which is some part of the program MPlayer. When I was watching DVDs some years ago, I used MPlayer as my basic like DVD player at my laptop, because now I don't watch DVDs so much, so I don't use MPlayer as well. But there is another executable called Mencoder, which can be used to convert between different codecs and different video formats, and add subtitles and remove something and add sound and things like that. But it can be also used to generate a file from a video file from series of images. And by some trial and error and Googling and other stuff, I somehow converged to this very complicated executable, which I have stored somewhere, and whenever I need some video I use this executable. So there are many different options, different codecs, different like a number of frames per second, some other options, and I will copy and paste it to Slack if you are interested, so you can try it. Otherwise there are probably many other different programs to concatenate images into an animation. And here there was exercise 3, which was flooding of the free energy surface. So Here was the like the exercise, and there were some blank points, something to fill. So in the first step, we loaded Metadynamics. We read the hills from the two-dimensional Metadynamics with two CVs, and we converted them to one-dimensional FreeEnergySurface. In the next step, we loaded hills for Metadynamics with just single CV, and this value was somehow made to start from 0, and then we generated some FreeEnergySurface which we called flooded, which was at the beginning same as the FreeEnergySurface from Metadynamics in 2 dimensions, and we used it as a kind of, like, I would say at the beginning, this FreeEnergySurface was kind of like ground truth. We used it as a correct FreeEnergySurface of alanine dipeptide with single CV, which is phi torsion. And then we tested whether this Metadynamics with just single CV, with just phi, can somehow correctly calculate the progress of or correctly flood this FreeEnergySurface. And we did it by, first we generated this function flooded, which was at the beginning same as this function, and then we added there some different hills from this one-dimensional FreeEnergySurface, and we plotted that. And from this we get a movie with the progress of flooding of the ground truth FreeEnergySurface from 2-dimensional Metadynamics by some tested short one-dimensional Metadynamics. And the question was how this one-dimensional Metadynamics performs. So what was the first to fill? So here there is just one CV, and this one CV is also periodic. So it was like the best option would be in the function C, which gives you creates a vector, the logical value true. It also works with just single T, like true. And of course you can use true in as a whole word, like in capitals. This is also logical value correct. So if you use one of these options, you were correct. Then what to do? Well, what to fill next? So it was necessary to fill how many cycles, or the indexes of cycles, and indexes of the first and the last frame to be summed up by FES function. So my option, what I did was I used 0 to 99, because this free energy or this Metadynamics contain 1000 hills. So if you used every 10, summed it in batches of 10 hills, then you would get 100 steps of the movie, 100 frames of the movie. Usually movie is something like 25 frames per second. Sorry, I had to switch the light on. Like 100 frames means like 4-second movie, which is quite reasonable. So my suggestion is 0 to 99 here, and then you have to use in the first frame would be in the first pass of the cycle, this imine would be number 1. So 0 times 10 is 0, plus 1 is 1. And the last frame here, Imax, should be 10. So 0 plus 1 is 1, times 10 is 10. Then in the next round, it's 1, so it's 11 to 20, 21 to 30, and up to 90, 990 to 1000. Of course, it's possible to do it in different way. So if you used 1 to 100, then you instead of I, you used I minus 1, and here you used I and plus 1, something like that. It should work as well. Maybe if you used some something which was wrong but not completely wrong. So for example, if you would use here 1 to 100, then you would just skip some very beginning. But visually, by naked eye, it would be probably not visible, but it's not 100% correct. So I think this is correct. Or maybe you decided to use each frame, so then it would be 1 to 1000, and here you would use I in both. This would work as well. So next, what is to be filled is this coefficient, and this is in a bracket 14 divided by 15 and with minus sign. So because we want to flood it not by the free energy but by the bias potential, and because we use well-tempered metadynamics, the hills heights are pre-scaled by 15 divided by 14. So we have to get it back to the bias potential. So we have to multiply by 14 and divide by 15. And so this is necessary to do. And minus, because we will have a bias potential, we need bias potential. So we don't need free energy surface, but the negative value, which is bias potential. Of course, if you replace this minus and then you use just 14 divided by 15, or you multiply it by 14 here and divide it by 15 here, all is correct. And you should get some result like that. So here is my movie, 4-second movie. And here is my movie where I used every single hill. So it should be something like 10 times slower. But it's nicely visible, the progress of flooding. So what would you say? Is there any hysteresis? Is there any problems with convergence or with some accuracy? I would say it looks quite reasonable because it's just 1000 hills, so 1 nanosecond metadynamics, very slow, very short. But here you can see, for example, that there is some free energy difference, and this free energy difference, if you look at this scale here, is but it's bias potential, so it's not free energy surface, but it's very similar. But here the difference could be something like 10 kilojoules per mole, maybe even a little bit more, like 12 kilojoules per mole, which is quite a lot. So, but because it's a very short simulation and just one collective variable, it's quite a good result. But for some some predictions, making some predictions, the error of some 12 kilojoules per mole is quite a lot. But this flooding looks quite well. So I would ask you, did you get some similar movie? I will switch here to see you a little bit. So did you get a similar movie?
Yes, I get a similar movie like this one.
Mm-hmm. And how did you somehow connected movies, individual snapshots to movie by some program, or you kept it like as individual files, or what is your experience?
I used the FFmpeg.
Yes, yes.
And it was all in Stack Overflow, so
Okay.
it was pretty much easy.
Okay, great.
No more.
So someone else, some experience, was this explanation of this what to fill, was it clear, or are there any doubts, or somebody had some different solution which may be correct?
It's clear. I have the same solution.
Great. Good to know. So I hope you will find it useful for such animations or some analysis or things like that. And the final exercise was like reweighting. So just to explain a little bit like how this reweighting works. So here I have some very simple like illustration that we can imagine having such a free energy surface with two minima. And let's imagine that we start metadynamics, very short one, during which we start from this minimum A, this minimum on the left side, and we flood it by the bias potential. But we don't flood it enough to jump to the minimum B, to the minimum on the right side. So we get such a flooded bias potential. And now we will run the simulation of the same system. We will do the exactly like the classical MD simulation, in which this bias potential accumulated by metadynamics is somehow preserved. So it's there. So it's flooded like that. So this would mean that these points on this flooded surface would be quite equally sampled. Then here it is a little bit higher, so it would be sampled a little bit less. And then here this minimum will be massively sampled. So if you take these probabilities, you, for example, make some histograms. For each histogram, you count how many times it was sampled. So you convert it to probability and you calculate the free energy from probability by minus KT logarithm of probability. Then you would get the profile, which would look exactly like this on this part. And then it would follow the surface of this bias potential, and then it would continue this way. So, and if you know, for example, that some points here were sampled in the presence of such a bias potential, you can take this free energy and you can like subtract this bias potential, and you can get the original profile. Or, which is kind of equivalent to doing this, is that instead of taking these samples here like as an equivalent, you weight them by E2 plus bias potential divided by KT. So for example, these values, these samples everywhere here would be sampled by the factor of 1. They will have be equal weights, all these samples in this region. But here it will be again like weight 1. But here this weight will be E2 bias potential divided by KT. So it will be something more than 1, some positive value. So the samples here will have higher weights. And if you do this and you calculate from these samples some averages, some probability distribution, and you convert it to the free energy surface, then you get the original free energy surface. So this is the idea of umbrella sampling reweighting, and it's used in many different free energy modeling methods. There is a small problem with metadynamics, which is that the bias potential during metadynamics is not constant. It's somehow constantly growing. So it's not possible to use this method for metadynamics. It's necessary to use some like extension of umbrella sampling reweighting. And there are many extensions. For example, Max Bonomi has made one extension like that. And the one which I used in this tutorial is by Pratyush Tiwari and Michele Parinello from 2015. And it somehow like compensates for the fact that the bias potential is like constantly growing in metadynamics. So how does it work? This is the exercise. So in this exercise, again, we load Metadyn miner and we save bias factor, number of frames, and temperature to some variables. By number of frames, I mean like number of, I will divide the length of simulation. So it was 1 nanosecond simulation into 50 sectors or 50 parts, 50 blocks. So each block will have 200 picoseconds, 200 hills. And then I load my hills file. It's the one-dimensional hills from one-dimensional metadynamics, where I use the psi as a torsion angle, as a collective variable. So the idea, I can maybe make here go to some plot of free energy surface. Yeah, this one. So idea is if we accelerate only motions on the horizontal axis, along the horizontal axis, would we also, or would it be sufficiently sampled this vertical axis? So in the previous test, we did like opposite. We accelerated sampling of CV1, and we were interested whether CV2 is somehow reasonably sampled. Now we accelerate CV2, and we are interested whether CV1 is reasonably sampled. So how does it work? We load these hills from metadynamics, and first we calculate free energy surfaces for 50 different frames. So at 200 picosecond, 400 picosecond, 600 picoseconds, up to 1 nanosecond. This value step converts this frame ID to this number of frames. So for example, if this I is 1, then this should be 200 for 200 picoseconds or 200 frames. And for 2, it's 400 and so forth. And for each, we calculate the free energy surface, but just from the first loop, it is first passage of this loop, it is for 200 picosecond, from 0 to 200 picosecond. In the second one, it's from 0 to 400 picoseconds and so forth. So we calculate only one, like 2% of the simulation, 4%, first 4% of the simulation, first 6% of the simulation, and so forth. And we convert this, we take from this free energy surface all values, like along the both axes, and we convert them to probabilities and sum them. And we do the same, like once we do it at the a real temperature of simulation, and once we do it at this well-tempered tempering temperature, which is the temperature multiplied by bias factor. And why we do that? So we are interested, we want to somehow calculate how this total bias potential is evolving with the simulation. So we in this method, we somehow separate the bias potential into two parts. One which is like a constant or not time dependent, and the second one which is time dependent. And this time dependent is that the bias potential constantly grows, and we can somehow compensate for this. So by this we calculate how does this bias factor grows, and then we do it like here at this point we prepare like empty vectors with 50 times 50 elements, each of it having value 0, and here we replace them by these results of this function. And at the end we divide these two vectors, so this will divide element wise, so it will divide the first element by first element, second element by second element. So again here we got the vector of 50 values. You can maybe try to print or plot this vector here, and you would see that it's like constantly growing. So it means that during the metadynamics, this bias potential is being constantly added, and this time-dependent part of the bias potential is growing. And in the next step, we load the file with collective variables. And I run the simulation to print this colvar file, where in the first frame, first column, there is time. It is sampled much densely than hills, so we got 5 times more values than the number of hills. So this is time, phi, psi, and the bias potential. At the beginning, of course, bias potential is 0. So after the addition of the first hill, there is some bias potential. And what we do is that we read this file, and first we convert this collective variable, which is from -pi to +pi, to some integers from 1 to 64. So we make some kind of histogram. We want to make some kind of histogram. So this is kind of bin ID. So here, this square bracket, comma 2 means that from this value, we take only second column. So the second column is the value of phi. We add pi. So originally it was in radians, so it was from -pi to +pi. And when we add pi, it is 0 to 2 pi. When we divide by pi, it is from 0 to 2. And if we multiply by 32, it's from 0 to 64. And the function floor rounds to the lowest integer. So then we would reach the values from 0 to 63. And when we add 1, it will be from 1 to 64. So this is like when we divide the free energy surface or collective variable into 64 bins, this will get, by this we will get the bin ID, bin number. And at the same time, we extract from this colvar the column number 4, which is collective, which is bias potential. So in the input, I use the option that I want to print bias potential. This is very useful for all different types of post-processing by rerating. So you better do it always, like it will not slow down your simulation, and you can use it in future. Of course, it's possible to somehow recalculate it by some PLUMED driver in principle, but it's no reason to not to save it, not to print it. The bias potential is multiplied by 1000 to convert from kilojoules per mole to joules per mole, and we create a vector with zeros and 64 zeros for probabilities. And then we cycle along these collective variables. For each line of this Colvar file, we determine which step it is. The step is from 1 to 50, so it corresponds to this frame. So we calculated this 50 correction in 50 different frames. So this will tell us which correction to use, and we increase probability for each bin. So for example, if the value of phi torsion in the first column is very, very low, then this CV1 would be some low number from 1 to 64. So it will be, for example, 2. So then the probability of the second bin would be increased by exponential to plus bias divided by KT. And like without this, it would work for some methods with some constant bias potential, but in metadynamics we have to add the correction for constant evolution of the bias potential. So we divide it by these pre-calculated values of these 50 pre-calculated values of the progress of flooding of the free energy surface of this time-dependent part, which is constantly growing. And after calculating this for all steps of the simulation, we convert it back to kilojoules per mole. We subtract minimum to get it from 0. Here I just replaced some infinity values where it was not sampled, so minus logarithm of 0 is like infinity. So I replaced them by some top value, and I plotted them as a free energy surface, and I used here some very, very simple trick that I generated free energy surface with 64 times 64 points in the free energy surface matrix, and I calculated it just from one hill, because immediately after that I replaced this free energy by what was calculated here. And it was plotted, and the value or the result is like this. So did you get some similar plot for this exercise?
Yes, I now understand better why I did what I did. This was the most difficult exercise for me, but I now understand better.
So so this looks pretty similar, like in this part, it looks pretty similar to this free energy surface here. Sorry, no, from this movie. So it looks pretty similar to this part here. Up to here, it's quite okay. But this part was absolutely not sampled at all. These positive values of phi were not sampled at all. So the conclusion is that, which is quite expected, that by acceleration of conformational changes in psi torsion, it's not possible to accelerate also phi, or there is no sampling of some other values of phi. So is it, are there any questions? Is it clear?
Yes, thank you.
So this was a little bit more advanced use of more advanced analysis of metadynamics and more advanced use of Metadyn There was it was necessary to touch some functions, like to go inside some objects, like FreeEnergySurface object. I hope it will be useful for your work. What I would also like to mention that I am aware of the fact that not everybody is very happy with R, and not everybody is going to be some user of Metadyn. So to little bit compensate it, we started, it's still in some like trial version, this website called metadynreporter.cz. You can try that. So there is a program which is called Galaxy, and it was developed mostly by people who are doing some next generation sequencing data analysis and things like that. And there are different Galaxy installations around the world for some general as well as specialized tools, mostly in this area, but also in other areas. And the idea is that you can here register, you can get your login and password, then you can log yourself in, and you can record or upload there some data, and data will somehow appear in this side of the plot. And then you can use here some kind of like workflows. So, but here we just have some Metadyn reporter, which is some basic use of Metadyn. So there is quite limited options, but we are happy to get some input from you. So you can start here some analysis of your data, and this is in this Metadyn reporter. It's just a very basic analysis of metadynamic simulation from Hills file, what we did so far. So so there is some calculation of free energy surface, identification of minima, plotting of this free energy difference as a function of time, and some other reports. But as I said, we are happy to put there add there some other functionalities depending on your demand. And the output is some PDF document, so you get some PDF report where all these commands from Metadyn are reported. So it's exactly available what was done, what kind of analysis, what were options, what functions you used, what were some settings of functions and things like that. So you can try. We would be very happy for any feedback. So that's all from my side up to now, and I would be very happy if you have further questions to answer any question. So feel free to ask anything regarding the program or some calculations done so far, or the exercise, or if you have some hints or what to add, some functionalities.
I don't have any question.
Great. Maybe I would comment like or add something like we would be very happy to add something for some statistics, for some getting more like free energy differences with some error bars and getting some statistical evaluation. So the method currently supported mostly by PLUMED people is, as far as I understood, block analysis, which is, in my opinion, not very good method, but the best available method. It's not very intuitive, not very like easy to use. There is some kind of like a manual input or some decision has to be made, and but the problem is that nobody came up with something better. Is my opinion, and we are trying to maybe come with some to try to develop something, some improvement, something which would be maybe less or more intuitive, or not without some like personal input. So we will. You can follow us. You can check Metadyn miner time to time, and we will do our best to somehow add some new functions also in this direction.
I have a question about the weighting method.
Mm-hmm.
And is it possible to use umbrella sampling to reweight? Is correct, or is a mistake?
So I mean, if you do not do this correction.
Yes.
So it's the problem is that if you because the bias potential is growing constantly, then the weights of some samples which are sampled at the end of metadynamics have higher weights than those which are sampled at the beginning. And as far as I know, you can do some like you can introduce some systematic error by omitting this. And definitely by doing this reweighting, you got much nicer result.
Okay, thank you.
So it's if you have some results already analyzed by some umbrella sampling reweighting, and then it works to try to reanalyze them by this reweighting with this correction. So
thank you. Okay.
I'm not at the moment 100% sure whether it's this error which is introduced by omitting this correction is like somehow like more like statistical or more like physical based, but I think you can introduce both types of errors, like that you completely like bias the free energy surface. I mean, like that you introduce some systematic error as well as some random errors. So it works to try.
Yes.
Editors will like it, reviewers will like it.
Okay.
Some other questions? So if not, thank you for your attention. I will stop sharing the screen. Okay, now I'm back in the screen mode. And thank you very much and goodbye. Enjoy.
Thank you. Goodbye.
Bye.